Thank you for the introduction. I'll just jump right in, since this is essentially going to be a continuation of the previous lecture. There was to start with, let me just remind you where we were. I asked these questions that I wanted to explore about describing and classifying active matter based on symmetries and conservation laws, which is sort of natural kind of question to ask for a physicist, and to try to see what sort of universal properties that you can have for active matter that are independent of the specific model details or the specific physical systems you might ask. And then I wanted to mention these topics of topology and non-reciprocity, especially relevant in the field of active matter. Right. So where we were was, I had this table of different classes of active matter, and I got through the first three. So I'll start today by going through the fourth class here, which is chiral active fluids. And then I'll talk about topology. I'll introduce topology and tell you specifically why continuum descriptions of active matter naturally lead to topological tools. And finally, I'll start on active solids today and continue into the last lecture. Right, so chiral active fluids, right? Why is it sort of a separate class? And one way, I like to think about them through this painting by Salvador Dali is in terms of the breaking of time reversal symmetry, which is of course common to every type of active matter system, right? That's something special, but that wasn't a symmetry that we discussed previously, right? We sort of talked about spatial symmetries in polar and pneumatic active fluids. But chiral active fluids have, of course, a handedness to them, right? Kind of left-handed versus right-handed symmetry. That's what is meant by chirality, but maybe more fundamentally, they sort of break this time reversal symmetry that leads to interesting properties in their hydrodynamics. And sort of to introduce, to remind you, we talked about things like self-propelled particle models last time, but what chiral active fluids have are some sort of chiral particles that are also active, and sort of the simplest version of that has both chirality and broken time reversal symmetry is a rotating particle or an active rotor, right? The active rotor, unlike this self-propelled particle, which has a force acting on it, the active rotor has a torque acting on it, right? A torque out of the plane in this two-dimensional case. And there are lots of examples of systems that have that, both sort of biological and synthetic. I just gave, some examples from a long time ago, but I'm sure there are lots of more recent ones. There's a particular example that I actually already mentioned yesterday that I wanted to focus on, though, which is this colloidal realization. This is the same one, actually the same system that I talked about in the case of solids or crystallites that it can form. So these are colloidal cubes in this case with a magnetic moment that are placed into an external magnetic field and sort of spin around on a glass slide. But in this case, what I wanted to focus on now is a sort of fluid state for these colloids. And you can kind of see that in a video here where you can tell at this micro mesoscale that you're really forming a fluid, and you can kind of zoom in onto a single droplet and see how the colloids flow around. But you can also speed up and zoom around in this fluid picture, right? Because you have colloids and you can have many of them, and look at the sort of continuum scale, right? This is a sort of coarse-grained scale where you can no longer see the individual particles, but you see that their collections, right? Which have an effective kind of attractive, cohesive force, right? Behave like fluid droplets.
Anton,
right?
how do I think about persistence in the self-rotation? self-rotating elements, do they flip and rotate in the other direction?
In this case, the chirality is kind of externally imposed, right? So they all rotate in the same direction.
In the same direction.
And I think most examples I'll tell you about it. It's like that. You can, of course, both have mixtures, right? Where, let's say you have 50-50 right and left, which wouldn't be chiral, but if you have a slight asymmetry, then it becomes chiral. Or you could have particles that flip as well, right? But the sort of, I guess, homogeneous population where every particle rotates in the same way is or maybe the simplest case, the most chiral, the maximally chiral case. Yeah. Oh, they artificially created it by tilting their slide slightly, and these because these particles are not density matched, right? They're quite heavy because they're made out of iron. They sort of naturally have a density gradient than in a gravitational field. Oh, yeah.
As these sort of separate, I guess, clusters of the particles sort of change shape and mesh together, is there some sort of like perimeter maximization or minimization that's happening over time, or?
Yeah. I mean, I would say that it's a very good question. I would say that very naively, just by looking at the video, it does seem like it's it has an effective surface tension, right? The droplets do tend to be circular overall, and you can this sort of very naive picture of surface tension, which is that particles attract each other, you have that here, right? The particles like to be near other particles, which is why they form coherent clusters. It's actually a very simple way to understand why there's this attractive force, which is that if you have these two, now kind of looking down, right? If you have these two magnetic dipoles, right? They're both rotating, right? And let's say they're perfectly aligned here. What happens is that they go through essentially these two configurations, right? Where here they're repelled, right? Because two dipoles align this way repel, right? If you think of them as the like charges are at the top and the bottom here. Whereas here you have, the dipoles attracting because, again, the unlike charges are closest together. But the attraction here, if you actually compute for a dipole, the attraction here is larger than the repulsion here. So averaged over a period, you get these particles to come together. And so there's a kind of natural sense of surface tension, but there's lots of other things going on, and so there's lots of interesting things in the system that aren't just pure attraction. And so maybe one of those things that you can look at, that you can measure in the system, is the dispersion of surface waves, right? So these are kind of like waves on top of on top of the ocean. That you have here, but in this case at the boundary of this two-dimensional, the one-dimensional boundary of this two-dimensional fluid. What you're seeing is a kind of couple of wave phenomena. One is that they seem to be traveling waves, which is already interesting in terms of the fact that this is an overdamped fluid, right? This colloidal system is not inertial, and so the fact that you have propagating waves is already surprising. That comes ultimately from activity, but then it turns out that if you kind of measure their dispersion relation and including the real and imaginary parts, right? So the dispersion tells you about the velocity of these waves as well as their decay time, right? You'll find interesting kind of new hydrodynamic coefficients that aren't allowed in equilibrium, right? And one of these is what I wanted to talk about, this odd viscosity coefficient. That's sort of necessary to understand these surface waves. And so this was, I would say, the first or among the first ways of measuring this odd viscosity coefficient. It's the first soft matter system. There turns out to be a kind of analogous systems in hard condensed matter and electronic physics, which is electrons in graphene in a magnetic field that also behaves like a chiral active fluid in some sense, or a time reversal symmetry broken fluid, where this odd viscosity coefficient was measured at around the same time. And finally, there's lots of other things going on that are probably too complicated to understand, at least. And an intuitive picture that I think there's some interesting modeling of these. So for example, if you have a thick slab of this fluid, it's kind of happy as it is, but as you make this slab thinner and thinner, eventually it will break up into these little droplets here, right? And this is, in some sense due to the fact that you have this chiral active fluid in it, right? This wouldn't happen for a passive fluid. And the chiral active fluid has some flows in it, right? You can have a flow even in the steady state. And this flow leads to this instability, this droplet instability.
Let me ask you something very quickly. How do you make this lab in the first place? How do you control the thickness of this lab? Because I thought this was self-organized in some way. That.
Yeah, good question. I'm not sure how they did this in this particular situation, right? But there's all sorts of, I guess, fluid tricks you can do. You can kind of work with it the way you work with a fluid. All right, so I already mentioned this this one realization of odd viscosity, the spinning colloids. I've briefly mentioned this graphene in a magnetic field here, but there are also actually other examples where these kind of anomalous chiral coefficients have been measured, and in fact the first measurement that I know of, at least, is this plasma in a magnetic field that also has all of these same ingredients, right? It breaks time reversal symmetry and chirality due to a magnetic field, and this measurement of odd viscosity dates back actually to the 1970s, before they really knew what the term odd viscosity or Hall viscosity wasn't even coined there. They, I think, called it something like anomalous viscosity that they found. And finally, even there are even biological examples that that have these ingredients. All right, so what are these kind of, so we're still thinking about the largest scales here for this fluid, right, the kind of continuum scales. So we want to try to understand what sort of anomalous coefficients in the description of the fluid you could have here, right? And I mentioned, the word viscosity already, and I kind of wanted to go back to understanding where viscosity comes from, why you can have this anomalous viscosity if you break time reversal symmetry, and then talk a little bit about the consequence of what sort of phenomena is this odd viscosity responsible for. So intuitively, viscosity is a resistance to some sort of strain rate. You pour a fluid into a container, right? It will quickly adopt the container shape if you're at low viscosity, but slowly if you're at high viscosity. In particular, if you have honey, here it turns out that your viscosity will be around the same as electrons in graphene, which I sort of like the analogy of. One thing that again tells you is that the fluid is described by just a few numbers, right? And those numbers you can measure. Rheometry is the sort of technique for it, where you shear the fluid in some way. In this case, it's a plate-plate rheometer, where you rotate the top plate, the fluid has to flow relative to the bottom plate, and then you measure the resistance, right? You measure how much torque the fluid exerts on the top plate. But in a more sort of abstract way, the way that you can think about it is that there's some sort of a strain rate in the fluid, right, which is the gradient of the velocity field with respect to a position, or you can call it a deformation rate here, and then you can relate this strain rate to the stress in the fluid, which the gradient of the stress here. like in the Navier-Stokes equations we wrote down yesterday, gives you an acceleration or a force. And so you can do this, in principle, if you have a viscoelastic fluid, you can also have a stress that depends on the deformation. We'll get back to the idea that, the deformations can cause stresses when we talk about solids, but for now, we'll think about this strain rate, stress, proportionality, right? And so what you have here in the fluid stress is a pressure term that we'll ignore, and this proportionality between the strain rate and the stress. And because the strain rate, right, is a gradient of a velocity and therefore has two indices, right, two coordinates that you can pick, and the stress is also a matrix with two indices, the proportionality here in between them is a rank 4 tensor, right? It has 4 different indices, and this is the viscosity tensor. Yes, please.
Hi, Anton. My question is, can we treat the surface waves of colloids like the helical edge states of topological insulators in the sense of trying to put topological ideas through dealing with the characteristics and to maybe attach a flux idea to this and so on, maybe think this viscosity like soft matter type of topological insulator because of the surface waves.
Yeah, I really like this question. I will show you some connections between autoviscosity and topology for sure. I think that maybe the surface waves isn't the clearest way to see this analogy, but there certainly are analogies with topological insulators that I'll get back to, and interesting things that happen at the boundary of these fluids.
Thank you. If the fluid is isotropic, why do we need different shears, shear 1 and shear 2?
Oh yeah. I'll get back to that in a little bit. So the two shears there are identical, right? In the sense that things shouldn't matter on which way you shear, but in order to describe the full kind of space of different flow, you have two orthogonal shear directions, right? So in particular, what isotropy gives you is the fact that in equilibrium, so you have just these two, maybe I have, okay, these two viscosities that give you the proportionality between stress and strain rate, and one of these has to be, it has to be the same viscosity coefficient on both of these diagonal elements, because those relate the two different shear directions to the associated stresses, right? If you were not isotropic, you could have other components. Yeah. All right, so this is where I was. So you have these two. If you are two-dimensional isotropic, and now I've made one extra assumption, which is that you're an equilibrium fluid, right? You're no longer active. Then the viscosity tensor can be written out in terms of just two numbers, which helps a lot, because otherwise you'd have all sorts of coefficients here. And these two numbers have a name. One is called the shear viscosity, and one is called the bulk viscosity. And furthermore, really, all we really ever measure in a rheometer is the shear viscosity. The only way you can measure the bulk viscosity is if you have compressional flows, right? If you have flows that include the divergence of the velocity. So by the way, I didn't really explain this notation, but you can rewrite the two indices of this strain rate gradient in terms of a kind of column vector by sort of flattening this matrix. And in this column vector, then you have four different components. One is the volumetric change, right? The compression or growth of a piece of element of fluid, rotation rate here, and then the two shear rates that are, well, they're orthogonal in shear direction, which means they're 45 degrees to each other, right? And you can do the same thing with the stress tensor, right? Put in the same coordinates and you get kind of the analogous things. So the top row is the pressure, the second row is the torque, which is the anti-symmetric component of the stress, and then the last two rows are the stress, the shear stress directions. So for example, the bulk viscosity relates the rate of volumetric change in the fluid to the pressure, right? And the two shear viscosities relate the stress, the strain rate in the shear space to shear stress. All right. So one example where why does the viscosity matter? Well, other than putting it in a rheometer, one other way to measure it that actually includes the bulk viscosity is to look at density waves. Right? Density waves are by definition compressional, and so if you have sound, right, in a fluid and the sound doesn't scatter, but it simply attenuates, right? The viscosities, what the viscosity lead to is energy attenuation, right? So your amplitude of the sound wave will decay in space, and it will decay with a decay constant that's proportional to a linear combination of the shear and the bulk viscosities. So here both of the viscosity coefficients come into play. But maybe the more important thing about this example is the fact that it tells you some of the intuition about what viscosity does, which is that it has to do something with energy decay. We kind of naturally associate with it. And one of the interesting things about odd viscosity is that it breaks this intuition. You can have components of the viscosity tensor that are energy preserving, right? But you can only do that out of equilibrium. All right, so where do these extra components of the viscosity tensor come from? Well, to understand that, let's go back to equilibrium and see why does this proportionality matrix have to be symmetric, right? And in particular, why, the fact that it's symmetric, if you rewrite it in this 4-index notation, means that you can switch the first two and the last two indices on this tensor and not change the component, right? Where does this symmetry come from? Well, it turns out to be an example of what's called an Onsager reciprocal relation that's guaranteed by equilibrium and in particular by time reversal symmetry, right? In fact, Onsager did a lot of things, right? He solved the two-dimensional Ising model, but it was actually the reciprocal relations that led to his Nobel Prize. So it's quite an important discovery, right? That these kind of transport coefficients, you can think of it as a transport coefficient in the fluid, have these symmetry relations between them. So now what happens when you no longer have equilibrium, right? When you start breaking the Onsager reciprocal relation, right? For example, by having a torque, right? And so breaking time reversal symmetry. To do this, right, one assumption that I'll keep is the fact that you are isotropic, right? So these rotating particles can still make an isotropic fluid, so you break time reversal symmetry without breaking isotropy, and you do get kind of net chirality instead. Well, one thing that can happen due to the torque is the fact that you have an anti-symmetric component of the stress tensor here. But that doesn't, doesn't have, that's not where the odd viscosity lives, right? That's in a different part of the stress tensor. Instead, you can look at still the symmetric component of the stress tensor, but ask what happens to the proportionality between the strain rate and the stress. And without time reversal symmetry, you can have the, Onsager reciprocity respecting component, which is the symmetric one, and the anti-symmetric component, right, which is the odd one, right? And so one way to think about odd viscosity is that it's all of the coefficients that are consistent with this anti-symmetry in the viscosity tensor. But if you kind of add isotropy, right, you reduce the number of coefficients that are possible here, and it turns out that in 2 dimensions you reduce it to just 1. There's only one way of writing out an antisymmetric rank 4 tensor here by using the 2 kind of isotropic tensors that were given in 2 dimensions. One is the Kronecker delta, and the other one is the Levi-Civita symbol, which is the sort of purely antisymmetric, right? Purely antisymmetric tensor. So now there's this single coefficient, right? That makes it a little bit easier to think about. That enters the viscosity tensor, but is odd, right? In some way, and this is consistent with our kind of symmetry-based arguments, right? So what does this coefficient do? Well, one way that's that I already mentioned, something that I've already spoiled, is the fact that this odd viscosity doesn't lead to any energy dissipation. Then there's kind of a more rigorous argument that you can use to prove that, but also maybe a more heuristic one, that if you look at, you substitute this part of the odd viscosity back into the stress, and then you substitute it into the equation of motion, into these sort of generalized Navier-Stokes equations, and you find that the force, right, in the y direction will then have a component that's proportional to the odd viscosity that depends on the velocity in the x direction, or the velocity gradients in the x direction. And so it's somehow transverse. Right? And so if you have a force that's transverse to the displacement, their dot product becomes 0, and you no longer have any energy associated with this term, any energy dissipation associated with this term. Another way to think about it that's still, again, heuristic, but maybe more symmetry-based, is the fact that this odd viscosity reverses its sign under time reversal symmetry, right? So kind of natural that if you spin all the particles in the opposite direction, the odd viscosity will have the opposite sign. But that also means that if you had energy dissipation in one direction, right, when you start rotating particles in the other direction, you'll have an energy growth that's exponential, and that's not allowed here, right? So the only way you can have both signs of the viscosity is to say that it's dissipationless. So I kind of mentioned this odd viscosity as the only thing that can happen once you break time versus symmetry, and I should maybe be a little bit more precise about it, which is that this is one of the coefficients that's allowed here, right? The other coefficients all have to do with rotation, right, in some way. So these 2 coefficients, this column in this generalized viscosity tensor, has to do with rotation rates of the fluid. And so they appear even if you start to rigid body rotate the fluid, right? Which means that they have something to do with the substrate that the fluid sits on, right? They can't be there in sort of in free space. And this coefficient here, which is also really, really interesting, that one doesn't have anything to do with the reference substrate, and instead relates torques to changes, volumetric rate of change of the fluid, right? Again, you need fluid compression or compressive flows to see it, but in practice, it's maybe a more natural coefficient to think about than these 2. All right. So I mentioned this, odd viscosity comes in based on symmetries, right? But I also wanted to give you a little bit of an intuitive argument for where it comes from, and there are now, models that have been developed kind of quantitatively to show that this does work, and where you can compute the odd viscosity either numerically or analytically from collisions, from particle collisions. But what happens when 2 rotating particles collide, right? And the special thing about this picture is that they're both rotating with the same angular velocity in the same direction, right? Which will only, the fact that this is a characteristic collision will only happen in a active fluid, right? So these particles are going towards each other, right? There's an overall center of mass for this collision, but when they collide, the special thing is that there's some sort of a friction at the surface, or some sort of stickiness between them, where they begin to rotate around their common center of mass.
Anton,
right?
can I ask a question?
Yeah.
Are they being attracted to each other, or just by chance?
No, this is just by chance. This is
Okay.
kind of a collision gas sort of picture where you can try to understand it. And so when these particles separate, right, the interesting thing here is that because they went from rotating around their own centers of mass to rotating around a common center of mass, there will be now a net rotation in this center of mass reference frame when the particles separate. And so this is a picture for converting this intrinsic rotation to overall fluid flow, which is essentially what this odd viscosity does, right? If the particles are rotating around their own center of mass, it leads to flows that depend on this rate of rotation. There's another argument that we can try to think about it for where odd viscosity comes from that's actually similar to the argument I gave for the duration of the Toner 2 equations yesterday from an inertial model. And so I wanted to reproduce that here, where we again have the continuity equation, and now I'm going to add an extra equation here, and our order parameter, sort of the equivalent of our order parameter here, is not the polarization, right? The particle, the fluid is isotropic, but rather the intrinsic rotation rate of the particles in this fluid. And there are various continuum equations that you can write out for this rotation rate, right? It involves convection, rate of change of this rotation rate, so the torque, the convection of the rotation, its diffusion through the fluid, and importantly, an active torque here, right? This is what creates a net rotation in the first place, along with some sort of friction coefficient that gives you a preferred rotation rate, right? And finally, what you should always have in this fluid is a coupling between the vorticity and this intrinsic rotation rate, because from the point of view of the particles, they're only rotating relative to their neighbors. So if there's already a vorticity in the fluid, right, you're measuring the intrinsic rotation rate relative to that. All right, so this is our sort of order parameter in some sense expression. And then finally, we have the Navier-Stokes equations. But the important point here is that we need to include some sort of a coupling between the Navier-Stokes equation than this intrinsic rotation rate that it causes. And there are kind of a couple of terms you could imagine. One is a antisymmetric stress term that I've already mentioned, right? That enters the antisymmetric component of the stress tensor, but also there are nonlinear terms that you can add that enter the kind of symmetric part of the stress. And the interesting thing about this specific version of the nonlinear coupling, where I've added, these stars here on the velocity to mean the rotation of the velocity field by 90 degrees, which is the same thing as multiplying it by a Levi-Civita symbol in 2 dimensions. So the special thing about this nonlinear coupling term is that you can imagine a fluid or a limit of a fluid where the density of the fluid is fairly low, right? So the collisions are kind of rare, but the relaxation rate of this intrinsic rotation to its preferred value is fairly fast, right? So the particles are mostly rotating with their preferred velocity, but then collide once in a while, right? Something changes, and then they go back to their preferred velocity. So when you go into this limit, what happens is that you can say, well, my intrinsic rotation rate is going to be constant most of the time. It's constant to a good approximation. So I don't need, I no longer have a dynamical equation for it. I just have a constant rotation rate for every particle. But what I generate from this, right, I kill then any gradients in this intrinsic rotation rate. But what I am left over with is a term of this form, right, where I have a Laplacian of a velocity now rotated by 90 degrees times a prefactor, right? And this prefactor is exactly the odd viscosity prefactor, right? If you plugged in the full tensor that we started out with into this equation, this is exactly the term that you would find, right? So this term tells you that the force in the fluid will be proportional to a Laplacian of a velocity rotated by 90 degrees with this odd viscosity prefactor. And this is why it's called a viscosity, right? It looks very much like the normal viscosity term, which is this one, right? Which just is the same form but without the star, right? Without the 90-degree rotation. So the other thing that this argument gives you is the fact that the odd viscosity will be proportional to the intrinsic rotation rate, or maybe a more precise way of saying it is that it's proportional to the density of the angular momentum, so the proportionality constant between the intrinsic rotation rate and the odd viscosity in this sort of heuristic model is precisely the moment of inertia of an individual particle. So this is the moment of inertia, and this is the angular momentum density, right? So the moment of inertia times the angular rotation rate. So we now have this kind of minimal model. Again, we were all about minimal models in the continuum here. Minimal model for a chiral active fluid, which is Navier-Stokes equations, right? These are now the Navier-Stokes equations plus an extra term, and this is just the odd viscosity term. And one thing you might ask is, what does this term do, right? What sort of phenomena do you have when you have this extra term? And one kind of interesting thing you can see immediately is that if you take a curl of these kind of generalized Navier-Stokes equations, you find, in 2 dimensions, a form like this for now the vorticity field of the fluid. This is kind of a standard way for solving 2-dimensional fluid dynamics equations. And the interesting thing about it is that you see the odd viscosity coming in here. Now I've divided everything by the density here. So this is the kinematic instead of the dynamic viscosity, right? So there's this usual kind of 2 viscosity notations, and you can do the same thing with the odd viscosity, right? And so here, the special thing about this term is that it comes in with a divergence of the velocity field, because remember we had this Levi-Civita multiplying the velocity field and the odd viscosity term, and then when you take the curl, you add a second Levi-Civita, and 2 Levi-Civitas is the same thing as a delta function. So if you have no compressive flows, right, in this 2-dimensional case, actually this isotropic odd viscosity doesn't affect the flow in the bulk at all. But it does affect the pressure, right? And one interesting kind of curious thing you'll find is that you can make vortices in this fluid where the pressure is reversed, right? So when you think about kind of inertial vortices, right, a hurricane, something like that, you necessarily have a pressure dip in the middle of the hurricane, and this pressure dip is necessary to balance the centripetal force for the fluid rotation, right? So you can make a model for a vortex that solves the Navier-Stokes equations. And you can ask, how is that different if you include an odd viscosity term here? And in fact, it is different, right? So without odd viscosity, this is the pressure profile you would get. But with the odd viscosity, even relatively small values of the odd viscosity relative to the normal one, what you can find is that if the rotation rate of the odd viscosity and the vortex is opposite to one another, you get a pressure maximum in the center, and now it's the odd viscosity that balances the centripetal force rather than the pressure gradients, right, the compression of the fluid. So you can even go kind of to an extreme case where you no longer have inertia in the problem at all, but still have a vortex here with either a dip or a maximum, depending on the sign of odd viscosity, where the vortex profile is then determined by this extra term. So this is sort of one kind of fluid flow problem where odd viscosity comes in. Oh yeah, and this is just showing which way things rotate relative to the vortex here. You can also have a kind of a different argument for what odd viscosity does if you think about boundaries, right? So when I made this argument that in the bulk you need compressible flows, I ignored the boundaries at all, but if you have boundaries, odd viscosity can also have an effect. And kind of a simple effect that it will have is that if you have a boundary, an inclusion whose boundary changes, right? And there's a certain rate of change of the area of the inclusion, then odd viscosity will cause a torque, a net torque on this object that's proportional to the rate of change of its area, right? And depending on whether the object is being compressed or growing, the sign of the torque will be opposite. Right?
Did we see these holes in the experiments, for instance? I don't remember seeing any inclusion there.
So in experiments they didn't do, so this is, you need to somehow measure the torque, so you need to have an inclusion in it, and somehow, and I don't think that's been measured, at least in that case. Let me actually skip this anisotropic case and go maybe more towards kind of why, maybe a more general picture of why and active fluids are interesting, not just, in fact, with odd viscosity, is that you can start to think about active hydraulics, right? So hydraulics is this ancient art of using fluids to make mechanical devices, right? The special thing about active fluids is now the mechanics is different. So maybe we can make different kinds of devices based on this hydraulics. In particular, if you have this property that you couple vorticity and pressure, or torque and pressure through odd viscosity, this begins to look like a very simple kind of mechanism, right? Which is a crank, right? A crank is precisely something that converts linear motion into rotational motion, and if you simply fill a channel with fluid and start pushing on it, you will get a torque response out of it from an active fluid. The other case that I'll also kind of skip, mention very briefly, is that you can go back and think about compressible flows in the active fluid case, and this is an example of a simulation of a compressible flow. And what you see here is that the effect of odd viscosity, the difference between kind of this shock wave in an odd viscous fluid and a shock wave in a normal fluid is not here. So this ux is the velocity along the piston, right, in the x direction here. That's kind of the same as in an equilibrium fluid. But what changes is that there's this transverse flow in front of the piston, right, and it has this kind of characteristic shape where, in fact, changes sign, right. On average, it's kind of flowing up near the piston and down farther from the piston, and this turns out to be the effect of the odd viscosity, right? Is transverse to the forcing, which is kind of intuitively makes sense, and there's a characteristic shape for these shock fronts where you can measure, and you can measure the odd viscosity by fitting to this characteristic shape. So these are kind of some of the interesting fluid phenomena that chiral fluids have. This is just, by the way, deriving what this shock wave looks like, and maybe going back to this picture of collisions where you can understand why you relate this transverse flow to the intrinsic rotation. But since I've already used up a lot of my time today, what I wanted to do was to kind of switch topics a little bit now, or connect things that seem maybe not so obvious, and go into the topic of topology, right, which is a very natural language to think about kind of continuum theories and their structure, their properties. So topology, there are various definitions of what topology is. a kind of a physicist definition, right, is that it's the study of properties that remain invariant under continuous change. I would say the mathematician would also need to define what continuous change is, and I will not do that. I'll sort of give you a more intuitive definition to say that, you know, a coffee cup can be turned into a donut through continuous change, and a cow can be turned into a sphere, but you have to make a hole in the cow to turn it into a donut, which is somehow not continuous, right? It involves cutting. So what does this have to do with fluids, right? It turns out that, you know, there's a particular study of within topology, right, called the homotopy theory, which will be particularly useful to us. And homotopy theory tells you something about how you can define integer invariance in a theory, and I'll tell you a little bit more about the kind of integer invariance you can define. That will, again, be invariant under continuous change, and so will be invariant under small changes in the parameters of our model. And this is, of course, very useful because in these fluids, as I say, you know, one of their advantages is there are only a few model parameters, but in practice, there's still quite a few of them, right? And whether, if you have some properties that are invariant under continuous change, it's, very physically useful to understand, right? So in fact, what is homotopy theory, right? Why is that interesting? Well, these are in fact examples of homotopies, right? They are kind of continuous changes of surfaces in this case, or paths in a certain space, right? And what's nice about homotopies is that you can classify kind of the type of homotopies that are allowed within a particular topological space, within for example, on a continuous surface. And you do that through, I won't go into too much detail here, but you do that essentially by looking at how you can modify, kind of continuously modify a path, right? Whether you can shrink it to 0 or not, and what happens when you append kind of multiple paths to each other. So this operation of kind of appending paths turns out can be described by what mathematically is called a group. And a group is essentially an operation, right? In this case, the operation of appending a path with certain mathematical properties. I won't go into too much detail, but rather to say that as physicists we can use this, right? So mathematicians care about homotopy groups, and they've mapped them out. So this is in particular homotopy groups of spheres, right? Where you have the continuous paths on a sphere. So this is your surface that you're studying, right? This is going from a point, right? Turns out a point doesn't have any kind of homotopy structure, to a circle, right, which is the 1 sphere, the 2 sphere, the 3 sphere, and so on. And then you have these homotopy groups which somehow tell you how you can continuously change paths in this case of pi1, or in fact for pi2, how you can wrap a sphere around a sphere. So for example, the reason that this is a z, the z is a group of integers, right, is because you have something called a winding number, right? And a winding number tells you that you can wind a circle around a circle an integer number of times, right? You can do it once, you can do it twice, and you can do it with a minus sign by going the other way, right? And that's the reason that this entry is non-trivial, right? Similarly, you can wrap a sphere, a 2-sphere, right, around itself an integer number of times. That's maybe less obvious to see. If I had a demonstration, you can do that with a plastic bag and a tennis ball, right, where you you wrap the bag around the ball once, but then you twist the bag and you can wrap it again, and you can do that any integer amount of times. And then you have some, and by the way, you can't wrap a path, right, a rubber band around a sphere, because you can always kind of take the rubber band off. You can always shrink it to a point. So in fact, this entire part of this homotopy space is going to be 0. And then there are some interesting ones if you're curious, right? The fact that this upper part of the diagram is non-zero is probably the hardest one to understand. You have here, for example, the wrapping of 3 spheres, so spheres in 4 dimensions, right, on 2 spheres, our usual 3-dimensional spheres. And the fact that you can do that in an integer number of distinct ways is not at all easy to understand, and it's the way you do it is what's called the Hopf vibration, and this gets into very, very complicated topological things. But I wanted to do is do something simpler, which is talk about how topology is useful instead. And most of what I'll talk about actually has just to do with winding numbers, right? So if you look at a liquid crystal, right, which is through polarizers, you see these special points, and it turns out that for lots of fluid phenomena, there are these point-like features that can be understood using topology. So another one of these phenomena is your fingerprint, where you can see topological defects in it. And the way that you can sort of classify this topological defect is by wrapping a path, right, around it, and then seeing how, in this particular case, right, how the structure of the fingerprint changes around, right? If when you go around this defect, if you pick up a sort of net rotation of the lines, right, or in this case of your pneumatic director, you will get a topological defect. And at the defect itself, the order breaks down because it's no longer kind of well-defined. So in particular, in 2 dimensions for this pneumatic structure, you get disclinations at certain points, right? So as I said, topology means that it's invariant under smooth deformation, and you can see that for a particular defect here. So for example, if you try to rotate the defect in some way, it will never go away, right? It'll change how it looks, right? But you'll, eventually with enough rotation, you'll just get back to where you started. And so that's, a pneumatic example of these topological defects, but they also exist in other smooth structures, smooth descriptions, if you have a smooth field. So one example of this is dislocations in a crystal, right, which are defects in the smooth displacement field. You can have defects in the magnetization field and in these director field. So why does this have something to do with active fluids? Well, it turns out that the interaction between topology and active fluids is a particularly interesting one, right? So, for example, one thing I mentioned at the end of the last lecture are pneumatic, active pneumatics, right? Active pneumatic liquid crystals, and it turns out that if you put some topological defects into an active pneumatic liquid crystal, they will begin to self-propel, right? And the reason for this is that's kind of easy to see heuristically is the fact that this particular type of defect, this charge plus 1/2 defect, has a certain arrow to it, right? It's different kind of going this way than going this way, and it will generally propel, right, along this axis. And in fact, it's the sign of this active stress that I introduced yesterday that will determine which direction it propels in. This -1/2 defect, interesting, it doesn't propel at all. Right? And so I played this video for you yesterday, and you can start to see these kind of textures in the active pneumatic field in particular, right? What you see in this video is the appearance of a ±1/2 pair of defects. So the unbinding of these 2 defects and the flow of this +1/2 defect kind of along its axis away from its -1/2 partner. So one way to try to understand this very complex pattern-forming system, right, the kind of chaotic flows you have here, is through the unbinding of these defects and the self-propulsion of this plus half defect that kind of ends up stirring the fluid, leading to interesting chaos.
Those defects, they do guide this, any phase transition, because in the let's say, in passive system, they can do that.
Yeah.
They are just observed, or they play a key role in this type of
Yeah,
dynamics?
they play a key role, and it's just something that if I had more time, I'd love to give its due kind of attention. There's lots and lots of interesting things here when you make it active. So, for example, the transition to chaos, right, is exactly the kind of unbinding of these defects, right? If these defects cannot appear, right, or if they stay close together, then you'll have a fairly kind of laminar flow, right? But as soon as they start unbinding, it becomes all chaotic and hard to describe. But then also you can ask, how is that transition different? Because you have the self-propulsion of a plus half defect, and that turns out to be a really important question as well. There's a sort of modification of the KT transition that involves this, essentially the ratio of this activity to the diffusion of this defect as well. A great question.
But activity, so increase the number of, so the activity of the fluid increase the number of defects compared to the passive case, if that?
Yeah, it does, in the sense that, up to a certain threshold of activity, these defects won't arise, but eventually activity will kind of promote their creation, right? Because this is essentially, from a point of view of kind of Brownian motion, kind of temperature, right? This temperature here is zero, right? There's no kind of, all the fluctuations you see are purely active. All right. Oh yeah, so this is one example of topological defects. There's another example of topological defects in polar pneumatics, where they have, say, different structures. You can have these aster-like things where the polar order parameter now that are arrow-like push or pull on this central point. You can have vortices and so on. So in order to have this one, actually, you need kind of compressible flows. You need to have density variations, but these ones don't require any compression or extension, and you can kind of observe them very readily by just putting a polar active fluid. This is exactly the colloid experiment that I showed last time, where you have these rollers on a substrate, and where you see immediately is the appearance of lots and lots of vortices, and then the coarsening of these vortices into one larger vortex. Right? Now, maybe I'll rerun this video since it's a particularly nice one. So depending on, this is, and this is the appearance, this is a compressible case. This is the appearance of these asters, right, which are very high density regions of a particular, now this is a different kind of polar active fluid where they tend to clump. Right, so depending on the symmetries of the fluid, you get different kinds of defects that are possible, and then the continuum theory, the hydrodynamics, lets you predict their dynamics and the kind of textures you observe, the kind of patterns that you observe in these fluids. And I actually have a little bit of time still. So the rest of this topological fluids, this topological section, what I wanted to tell you about is a completely different kind of topology that comes in, and it's sort of relevant to a question I had earlier, which is, is there a relation to topological insulators, right? So topological insulators are topological in a completely different sense, where they can be kind of homogeneous in their in their structure, right? They don't have any topological textures, but there's still some way of understanding their behavior, their dynamics through topology by essentially looking at the space of waves or excitations of this insulator. And so what I'll show you in this example is if you take a chiral active fluid with odd viscosity, so this is one particular kind of theoretical realization that I like when you can think about a fluid of vortices, now 3D vortices, but then you think about the surface waves on top of this fluid, right? You can also this is just one such realization. And what you can start thinking about is the linear excitations, right? The linear properties of these surface waves, and seeing how topology can help you kind of predict what's happening there. Right. So in this particular fluid, you ask, well, what's the dynamics of this height field, right, for these surface waves? And it'll look actually very much like sort of linearized Navier-Stokes equations. You have this part, this divergence of the velocity, sort of the averaged velocity in the xy direction, averaged over the z. And you have another equation for the velocity field that's now modified by, and I'm going to add actually two chiral effects that are going to be both important. One is the Hall viscosity, or the odd viscosity that I already brought up, that multiplies this velocity by rotated by 90 degrees. And the other one's maybe a more intuitive one, which is the Coriolis force, right, which also breaks time reversal symmetry in the sense that it arises in fluids that are rotating as a whole, but isn't a viscosity coefficient, right? It's a kind of extrinsic property of the fluid. It's a property of the drive of the fluid rather than a transport coefficient within the fluid. Right? So you can write down these equations. There's another example that where you get the same exact form of these equations, which is if you think about compressible flows purely in 2 dimensions, right? Where you no longer have surface waves, but instead you have a density field, and you linearize the Navier-Stokes equations around a certain density and velocity configuration. You get the exact same equations, right? So you can think of them as acoustic or surface waves, depending on what you prefer. And now what you can do with these equations is you write them out in Fourier space. So I take now a Fourier transform in time to get a frequency prefactor here, and also a Fourier transform in space, right? And now we'll, these extra terms that have a broken time reversal symmetry will enter this kind of response, right, matrix between the that gives you the dynamics of the fluid, right? So it gives you the frequencies of the normal modes. Right, so the kind of typical normal mode analysis here would be to solve for the eigenmodes of this matrix, right, for the frequencies, and then you can plot them as a function of the wave number, right? Here, by taking the spatial Fourier transform, you get this, these Qx and Qy, which are the wave numbers, right, the Fourier transform, the spatial Fourier transform components. And the special thing here is that if you now plot these frequencies as a function of wave numbers here, what you'll find is that your band structure, right, your dispersion relation will have a gap between them. But the more kind of interesting thing about it is the fact that each of these bands, right, below and above a gap, you can compute a topological invariant and associate this invariant with this band structure, right? And it's invariant in the sense that if you perturb this band structure in some way, it won't change, right? It's an integer and it can't change. This is only, it turns out that it's only possible in a fluid if you have both the Coriolis force and the odd viscosity. I won't talk too much about that, but the special thing about the Coriolis force is that it opens this gap here. What the odd viscosity allows you to do is to compactify this reciprocal space and compute this invariant in a well-defined way. how you compute it is maybe, you know, not so interesting. There's a formula for this invariance called the Chern number. It's the same one that you get in the quantum Hall effect. And you know, you take the eigenvectors, right, the bands here. You take the associated eigenvectors, take a product, take a gradient, take a dot product, and take a curl in this reciprocal space, and then finally integrate this this Berry curvature you get for each band over the entire space. You know, when you do this, you can you get a number that depends on both the sign of the odd viscosity and the sign of this Coriolis force. So now, okay, so you can do this now. Why does this matter? Why do we care about this topological invariant that you compute? It's not associated with any defects here, right? Instead, what it associated with is that if you add a boundary to your fluid, right, and look at the dispersion of waves along this boundary, then you'll find some extra modes that come along here, right, that span this gap that we've opened up. And these modes, the number of these modes we had is actually precisely given by the Chern number. So for example, here you have one of these modes that I've plotted. So here you can drive the boundary of the fluid with a particular frequencies and see the propagation of this mode all around the boundary in a kind of a chiral way. So this is the direct analogy of these edge states of topological insulators, but now for a chiral active fluid.
Can I ask a question about the Coriolis force?
Yeah.
What is the origin? Where it comes from?
Yeah, so you have to kind of put it in by hand in order to get this theory. I mean, one way to think about it is that you can take this active fluid and rotate it as a whole. You take the bucket of it and start rotating it, right? And then the Coriolis force would come from going into the co-rotating reference frame of this bucket. Another way to think about it that's maybe more natural is that if you have this chiral active fluid, it will naturally have some sort of a steady state that's not necessarily, you know, zero velocity steady states. And in lots of examples, they really do form vortices. And so if you look again into the co-flowing kind of reference frame of this fluid, you'll get a Coriolis force.
So it would be a natural, let's say, a steady state of this fluid.
Yeah, exactly.
Okay. As a follow-up to that question, when you look at the same system in the non-co-moving reference frame, what happens to the topological invariant?
So it will disappear. So essentially what will happen is as you slow down the rotation, this band gap will close. And once the bands touch, right, there's no longer a good way of, you know, computing. Essentially, this formula becomes ill-defined because this formula is a curvature over a single band, right? And the point where they touch, you no longer have a, you know, way of resolving between them. So it sort of stops being a good invariant.
I mean, I understand this technical explanation, but you know, it's the same physical system. The topology of the band structure has you know, it has it affects the physics of the motion, right? Yeah. And you should see the same physics of motion resulting from the topology in the case where you're not co-moving.
Oh, you're saying in the different reference frames.
Yeah, exactly.
So yeah, I think you'll still have. I mean, I think the kind of the rotating vortex example is maybe a more intuitive one, where you really have, you know, when you're trying to linearize. The thing is that what you're doing here, maybe more precise, is that you're linearizing about something, right? And so if you want to kind of compute linear modes around a steady state, you necessarily need to pick the steady state, right? And if the steady state is, you know, not the one that you have, you'll get a, you know, you'll get a different, you'll get a wrong essential linearization.
No, I see. Thank you.
Yeah. All right. So what I didn't get to today very much at all is the active solids part, but I've already introduced it a little bit, right? And maybe I'll end this lecture by just introducing what I'll talk about tomorrow. So there are all these examples of active solids, some of which I've given, some of which are purely biological, right? And what we're interested in is the continuum description of these active solids, right? At the scales that's sort of much larger than a single atom, right? And particularly the mechanics of these, right, that we can try to describe. So here, for example, is a crystal of rotating particles. So you could imagine that chirality and breaking of time reversal symmetry now becomes important. But in addition, what becomes important here is the elasticity, right? So when we come back to these questions that I've asked to describe and classify active matter based on symmetries and conservation laws, we now have kind of a different symmetry, or I would say broken symmetry, which is the spontaneously broken translational symmetry of a solid that gives rise to its elasticity, right? And we can ask, given that extra feature, right, of elasticity, what do you get as universal phenomena, right? So similarly to how we talked about fluids, right, we're going to talk about solids where we have, generally an elastic medium plus active particles, but the active elasticity is the coarse grained description of both of them together, right? If you just think about the passive elastic part, what it gives you are sort of elastic interactions, effective interactions between the active particles. And what we're interested in describing are the large length scale and slow time scale phenomena that give rise to a continuum theory. Right. So why is that important? Why is that something that we want to do? Well, one reason is biology, right? Most biological things tend to be solid because they want to keep their shape, right? And in particular in developmental biology, right, nature does some incredible things, right, where it uses a combination of chemistry and mechanics to very precisely and robustly engineer shape, right? And not just kind of overall shape, but really where each of the cells are in this organism, right? So this is an example of what's called a hydra, right? And what you can do in a hydra is to kind of make it develop in all sorts of wrong ways. And it turns out that the way to make it develop in the correct way is actually to put topological defects on the surface of this hydra in terms of its surface texture in the right locations, right? If you put the right kind of aster and comet, so +1 and +1/2 defects in the right way, the hydra will develop into a correct shape. Otherwise, it will have these little funny shapes that they can develop. Another reason to kind of study active solids is sort of various applications that are more kind of technological. One of them is sort of robotic swarms, and what we'll talk about is very much a robotic swarm. This one is a kind of liquid one, or one that's programmed to sort of flow into a particular shape. But you could also imagine connecting these robotic swarms into solids, right? I already mentioned kind of origami, right, as another motivator, this self-folding boat, but that also has some technological importance through things like deployable structure, right? So if you want to have a tent that makes itself, or a satellite that can unfurl in space, you want to think about the kind of interactions between activity and elasticity. And finally, even at the level of a kind of single robot, you can have really interesting kind of interactions between kind of elastic and active components, leading to unusual motion. So this is a particular kind of active solid based robot that can crawl on its surface by kind of actuating these materials and just the right way. So I already mentioned the kind of the special ingredient here. The new thing is going to be elasticity, and elasticity is very much like fluid dynamics in a sense, right? It's also described by a tensor that's kind of analogous to the viscosity tensor. It's called the elastic tensor. But this elastic tensor now gives you stresses, elastic stresses, as a function of strains rather than strain rates, right? So the big difference here is this dot, right? So instead of deformation rates that we need to have interesting fluid-like properties in a solid, you have a reference state against which you can measure these deformations, and the deformations I'm going to annotate in much the same way, right, where you have kind of volumetric deformations and rotational, kind of rigid body rotations of your system, as well as the two shear directions of the solid. And now the same way that the viscosity was the relation between deformation rate and stress, the elasticity tensor is this proportionality, which in equilibrium has certain components. These are the bulk and the shear modulus, but out of equilibrium we'll have extra components, and these are the sort of odd elastic components that I wanted to emphasize in this active solid picture. So I already showed you kind of this video, right, which is the crystalline analogy of the active fluid picture, where due to elasticity you have now a new set of phenomena that arise, and you have this the same way that in a fluid you can have properties that are independent of microscopics. You can do that in active solid experiments. Right? You have these different platforms, all described by the same continuum theory. So what are these kind of platforms? Well, in terms of crystals kind of that form out of these rotating particles, you have lots and lots of examples, maybe even more so than for the chiral active fluid examples. I already mentioned starfish embryos here, the robotic case here. Turns out that mussels in many ways have this odd elastic structure, but now in a different way, where you have these molecular motors that process along filaments in the fiber and exert work. And so if you do some sort of deformations, special deformations of this muscle tissue, you'll get interesting active phenomena out of it. Other examples of notes are sort of maybe purely magnetic kind of chiral structures here called skyrmions, different type of colloidal systems that aren't based on magnetic particles, gyroscopes that you can put together in a lattice, or some sort of piezoelectric materials that you can make with the right sort of feedback. All right, so the point is that there's lots of ways of realizing these kind of same continuum elasticity theories, and they all rely on this basic idea that in equilibrium, the only, in two-dimensional isotropic materials, there are only two moduli that you can have. One is the bulk modulus, which is the sort of inverse of the compressibility of a fluid that relates the volumetric compression to pressure, and the shear modulus, which relates a particular shear deformation to the shear stress in the same direction, right? And if you break the constraint of equilibrium, you'll get these extra moduli. So the ones that I wanted to emphasize are the ones that aren't on this column, because these moduli tell you about stresses that you get due to rigid body rotations, and unless you have a substrate, you will not have these. Instead, these two remain even if you have no substrate, right? In particular, this odd elastic modulus tells you about torques due to volumetric change in the material, and this one couples two different shear directions, right? It couples shear in, let's say, along the horizontal to shear at 45 degrees. All right, so I think I will end here as a little bit preview. So what I wanted to talk about tomorrow is the sort of phenomenological consequences of having these, right, where they can come from microscopically, and then also some of our recent work that goes beyond the sort of linear approximation here, what happens when you think about nonlinear phenomena in active solids. Yeah, thank you.
Very nice. Questions for Anton?
Okay, thank you. Thank you very much for the presentation. I was really interested, particularly when I saw the defects on the asters. Okay, actually, do we have some similar defects to the asters where the directions are instead pointing outward and later on inward, for example?
I think the asters, the only asters that I know of are really where the flow goes inwards, because that kind of can be stabilized by, by elasticity, essentially, by crowding, where things kind of go in. I think this can form, and that's what happened in the movie here, so you get a very high density region here, right? If you had the opposite, right, it would just be empty space, and then kind of defining it as a defect, what is a defect of, right? There's nothing there. So I don't know of any examples of those, but maybe that would be an interesting thing to find.
Thank you.
Carolina.
Let me ask you one question, which I think is very simple, but I don't see. If I look at the third idea that you have, that pulling in one direction means that you do this. This is your third element.
Yeah, third. So this is in the elasticity tensor, this 0. I can.
Well, yeah.
This one, right?
Right. Yes. So if I understand well, what would lead to it? That would be like having a shear into different directions, right?
Yeah. So one way. So the reason that these are 0 is due to isotropy, right? So these. All of these terms can be present in an active solid as long as you break isotropy, because this one in particular is a shear due to a isotropic change in volume, right? Shear stress due to isotropic change in volume, and that means that you have to have a direction in the material that tells you which. Where will it shear, right? Or what direction will it shear into, right? Because your strain, you have kind of a isotropic strain, but the material responds in a kind of anisotropic way.
This would not be like this negative Poisson ratio, for example, which already happens without activity. I mean, this would be present, right?
Yeah, it won't be, right? So the fact the Poisson ratio is a combination that I won't try to reproduce of the B and the mu, right? Which tells you about, so this is kind of a relation between two uniaxial deformations, right? So here, to measure the Poisson ratio, you shear it uniaxially here, and then you measure the, the uniaxial strain in the perpendicular direction. Of course, active materials will also have that, right?
Okay, whereas here
but it will be
this.
purely, it can be purely kind of isotropic.
Okay, whereas here you say you do this, and the materials do that.
Yeah, you do this in here, you do this in the 0, you do this in all directions, right?
Okay.
But the material shears in one particular direction, so it has to have
that's the
thing.
difference.
But I think, one thing I'll talk about tomorrow, maybe the more special thing about these, right, is that you can really see that, unlike the typical equilibrium moduli, this bulk and shear modulus, you can extract energy. You can see that the solid is active as long as you put in a K0 and an A in there by extracting energy from it, right? It can, but I'll get to that tomorrow.
About the topological defects, for them to appear, we need yeah, maybe for them to appear, we need to exert some energy in the system, or by the active nature of it, they appear naturally?
It's a good question. So I think this is kind of quite system dependent, right? I wouldn't, like topology itself, which is very general. This question is very, very much depends on the details of the system. So in particular, in the pneumatic case, where I probably take me a little bit too long to scroll through it. In the pneumatic case, what you have is the spontaneous appearance of the defects due to activity, right? There isn't, let's scroll through. So, if the fluid is equilibrium, what it will want to do is to essentially align all of these filaments together. It'll probably form some sort of very ordered thing. And the only reason that the defects appear is because the activity is kind of pushing on these filaments around. But in other cases, you can have purely kind of passive generation of defects, or defects that are happen to be there being pushed around by activity.
But in that case, the activity generates the topological defects, but can erase them too?
In a sense, it can. What can happen is that these, the same way that these two these two defects, when they appear, they fly apart. Eventually, this one can meet another, defect with the opposite charge and annihilate against it. I wouldn't say that that's kind of activity annihilating it, but it can speed up the fact that this plus a half defect is going faster can speed up how long it takes to annihilate.
So this topological charge is conserved quantity.
Yeah, exactly.
Okay.
So that's the special thing about topology is no matter the texture, the precise texture here, the overall charge will be conserved. Yeah.
Okay, if there are no more questions.
One.
Another one.
Sorry.
The last one. Thank you very much for the lecture, Anton. Very nice. My question is how we can compare the activity in fluid mechanics, active fluid, for instance, with particle-based models like active Brownian particles, because in these two different models we have activity as well. So they have the same meaning, which is we are pumping energy inside the system. That's my question.
Yeah, thank you. It's a very good question. So I think the connection there is this kind of coarse graining procedure, right? Given a particular active Brownian particle are an example of a microscopic model for an active fluid, right? So if you have a few of these, then all you have is the sort of dynamics, right? But if you have many, then you can try to take up, right? What you do essentially is take a patch, right, of many of these active particles, and you say, well, what is my average velocity in this patch, right? What is my average density? And then you can try to write the continuum equations of motion for this fluid.
More questions? If not, let's thank Anton again.
Thank you.
Before we go out